Good afternoon, everybody. Am I audible to the people who are there? Uh, this is the live session of, of energy efficiency, building acoustics, and daylighting course. And we have received a couple of questions. We'll just address them before we try to solve a few problems. But the best is if you ask us some question, then we'd like to respond to those questions. That's the first thing. The questions those have come actually. One of them is related to how to calculate energy as per ISO 144040. Well, we couldn't find out anything as far as ISO 144040 because there's no reference towards energy calculation. But I believe if it is yearly annual calculation, annual cooling or heating load, then that would need a very robust calculation, and such a thing can only be done to various softwares such as Equest, Energy Plus, largely based on methods like Beans method. Some of them are based on Beans method. Some uses finite element and similar analysis for calculation of the heat transfer equation and so on. In our course only, we try to give some basics of the equation and their simple solutions, not meant for annual energy load calculation, because that would be very robust, calculated for 8760 hours, that is 365 into 24. So that's the thing. I really couldn't find anything related to 144040. Right? If you have anything specific more, if there's any, if you have gone through that code, and if there is any statement that you would like us to refer back and respond to you, we can do that. Another question was, what kind of ventilation was suitable for better lighting? I mean, lightening, I believe it is lighting in large buildings. Well, I don't think there is any kind of specific ones, but in the northern hemisphere, north side obviously provides you with good daylighting facility. If it is building other than, of course, industrial building, factory building, which can have skylights and so on. Northern side, north facing walls, they receive practically no direct solar radiation during daytime. Early in the morning in summer they do, and evening if you go away from the equatorial latitudes. So north side is a good one, and skylights are also usually towards the north. South, if you have, fine, you can have glass or large openings there, but then you'll have to have the shading devices so that it blocks the summer sun but allows the winter sun to come in. But sun means there's a chance of glare. So saying that which is the best, well, it's not very easy. You have to go by case based on the principle that we have talked about in the course, right? Well, how important is the energy efficiency in the field of civil engineering? Well, very interesting question, actually. More and more it's likely to be more and more relevant in the civil engineering in near future. Although this kind of energy efficiency issues are there for last about 30 years, but it seems to be picking up at an accelerated pace all over the world, and newer kind of facets are coming. So it's actually in the interface of architecture and engineering, but the physics, since a lot of physics is involved, therefore engineers can get involved into this, and it's very relevant because the cost, the overall cost of building, life cycle cost, the maintenance and operational cost, the operational cost part, and energy cost is taken independently as operational cost. So I think it's very important, and it's becoming more and more important. Now, if you look at the precast building system, which are becoming industrialized building construction or precast building system, which are becoming very, you know, kind of technology which are coming into the building all over the world, you'll find that sandwich wall construction with thermally insulating core or even insulated forms, right? So the form itself has got insulation on the outer and inner leaves already, so with a concrete core. So there are different kinds of construction technology, building, related to building are coming, and therefore it's very important. So it's extremely important. In fact, in my opinion, it's going to be even more important in near future. After all, sustainability is a big issue. Everyone is looking at it. Cement, concrete technologist, and building or water resources engineer everywhere. So it's very important. How to calculate wall solar azimuth angle and azimuth angle? Basic formula of this equations. Wall solar azimuth, how do you define? It is the, if I know the solar azimuth and if I know the wall azimuth, difference of these two would give you wall solar azimuth, right? So you see, if I may draw it like this, and let's say this is my geographical north, right? And the sun's projection onto the ground is somewhere here. Sun projection onto the horizontal plane is somewhere here. So this is sun's projection, right? Say sometime maybe in the morning, and my wall is facing, let's say for simplicity, south. So normal to the wall is here, normal to the wall is here, right? So wall azimuth is this, wall azimuth is simply this, wall azimuth, and this is the solar azimuth. The difference between these two is gamma. That's what I think the notation you have used. Gamma is the wall solar azimuth. I think that's the question. Wall solar azimuth angle. Okay, how to calculate solar azimuth angle and azimuth, calculate wall solar azimuth and angle of azimuth. Now, this is very simple. If this is your wall, normal to this is this onto the horizontal plane. So from the due north, this is the wall azimuth. If this is your wall, let's say the wall is facing, so then this should be the normal to the wall. This will be the wall azimuth. Now solar azimuth, there's a formula given. Solar azimuth, if you recollect from our slides, right? So solar azimuth angle was, how did we give it? I mean, this is, we used, this is altitude. It was, I think the formula that we used. Yeah, I think so. This is, did we use this actually or something else? Yeah, it was, I think we used cos. So this was cos AZ angle. That's what we have used, is equals to cos latitude. Cos latitude, I think, can I erase it somewhere? The pen. New page? Where is it? Okay, so let's use a new page. There's a new page. So cos AZ, I think we have used this, equals to cos latitude, then sine declination, sine delta, minus sine latitude, cos delta, cos hour angle. Cos delta, cos hour angle divided by cos beta. That's what I think it is. So this is how we have used it. So therefore you have to first find out beta. Cos beta you have to find out. Delta can be found out from the formula that you have given. Hour angle is measured from 12 noon. Absolute value, that's in our convention we have used. So this is one formula. There can be slightly different formula as well, right? And we have used this formula. The convention is it's measured from azimuth angle is measured from the north, right? Azimuth angle is measured from the north. So that's what it is. Now latitude is location wise. For example, if it is Delhi, it is 29 point something, whatever it is. So in India, it varies from around 8 to 32 or so. Thiruvananthapuram, near Thiruvananthapuram, it will be around 8 degrees latitude. And delta, there's a formula, no, right? Delta, there's a formula we have given, 23 point cos delta, was it? This was 23 point, delta is 23.45 multiplied by sine 360 by 365 plus n somewhere plus multiplied by 284 into n. So 284 plus n. So n is the number of days starting from 1st January. So, so 31 days in January, etc., etc. So first find out delta, latitude is known, our angle is known, then you have to find out the altitude angle. And altitude angle is given by this formula, sine of altitude angle, beta is equals to sine latitude, sine declination, minus cos latitude, cos declination, and cos of our angle. And this, in fact, we have derived it also from the fundamentals. This from the spherical trigonometry we have derived. So I think that is the answer to that question. And once you have found out the azimuth angle and the wall azimuth is known, the difference between these will give you the wall angle. Yeah. There's another question. Okay. Let us go to the next page then in the meantime. Situated at heart of a city, very congested. How to provide daylight inside? Very good. Now, first of all, you see, it's coming a new building, right? Or existing building. Now, the thing is that you cannot ignore the fact that functional design starts even from urban planning. Now, there has to be a minimum space between two buildings, even in a congested site. Now, if it's an existing building and there is no other way, like something like there are many urban villages, sometime in the relatively less planned cities, then you still want to give it. You might provide a courtyard. If you have for example, if you have the let's go to this. You can write. Yes, supposing this is the plot available to me, or this is my plot, and it's all congested with buildings like this, which should not be the case, basically. So building is there. This is my plot, and building. So what I can do is, if I'm planning it now, a building here, this is my plot, I can provide a kind of courtyard, right? And this courtyard should be right going up, and of course I have to have some amount of frontage, side, etc. left as per the bylaws. But assuming in an extremely unlikely case that nothing is available, so what I do is I provide a courtyard, and through the courtyard, in fact, I provide some daylighting. Or I can even have a chimney. These days you have daylight chimneys and things like that, through which you can allow some light to come in. Largely, it would be also if depending upon its height, so you can even you have to capture the light from the top, plan it accordingly, so you can capture the light from the top. Actually, you can provide a courtyard so that light comes in through that, and possibly you in tropical scenario you'd like to maximize the internally reflected component as much as possible. So that is the way, but it has to go case by case basis, right? Okay. The concepts of bringing in light through, modern, basically systems of chimney or something, is very much there today. One can use them. Okay. So any other question?
As of now, these are the questions.
Okay, so this is a question. So we can solve one or two problem. Let us solve one or two problem. One of the problems we thought that we might solve is right. What is the altitude angle of the sun? What is the question is what is the beta of sun at 3 p.m. right at 3 p.m. at location I must know at 3 p.m. on which location? What is the location that we fixed? What is the location? What is the location? 3 p.m. What is the location? Latitude angle I got to know. For which latitude we calculated? 28 degrees. So at 3 p.m. At a place L equals to 28 degree, right? North. Okay. And declination angle is already given, delta is equals to 10 degree. So this is very simple. Sine beta is equals to sine 28 degree, right? Sine 28 and sine 10 minus cos L, that is 28, and cos 10 and cos of hour angle. Now what is the hour angle at 3 p.m.? 3 into 15, 45 degree, cos 45 degree, cos 45. So this is sine 28 is how much? Sine 28 is, 0.469 multiplied by sine 10, 0 something, it will be very small. 0.1754, okay, minus cos of 28, 0.883 multiplied by cos 10, 0.985 multiplied by cos 45, 0.707. So if I find this out, sine beta will be equals to minus 0.32. So therefore, you find out the inverse beta. So beta value you have to find out. So it is at 3 p.m. as you can understand, right? 3 p.m. at 28 degree latitude. Sun would be somewhere there. Sun will be on cos 10. So sun would be somewhere there. So east it rises and it will be somewhere there. So altitude angle of the sun would be how much? Minus, how much is coming? Sine beta is
Minus 18.7.
no, altitude cannot be minus, that means it's not there. Somewhere there is a problem with the calculation. No, this cannot be. It cannot be minus. It cannot be. It cannot be altitude angle cannot be minus. So position is here. In the afternoon, altitude angle will be somewhere. Declination is 10 degree. That means it is somewhere around 10 degree means September, October, November, or something like that. Or declination 0 means June and September. So just before this summer, there's a small mistake, I believe. Sine of how much? Sine beta is equals to how much?
0.696.
So there's some mistake there. Which one? The earlier page. There's some minus there.
It's plus, sir.
This is plus. This is the plus. Yeah. So this is right. So this formula is wrong. Right. So sine beta comes out to be
0.69.
Yeah, that's right. Beta will be 44 degree,
14.
14 degree. So that's what it is. So this is how it is. So this is one problem which you can solve. Simple, not very difficult. Is there any question in between? Anybody has asked a question?
Yes, sir, no question.
Okay, so azimuth angle also you can calculate out same time. Now cos AZ was equals to cos latitude cos delta minus sine latitude sine delta, right? Cos our angle, sorry, cos, what was it? Sine latitude cos delta cos delta cos delta cos delta. Is there an eraser here? I don't know. It is there. Yes, must be there.
Third one is eraser.
Hmm?
The third one.
This one, right?
Yes.
Yeah. So this is just erase off. Go to the pen. So this is sine latitude, right? And cos delta, and then cos our angle. And all this is divided by cos altitude angle. Now sine altitude angle was point.
It's
This,
not getting.
hmm?
The picture is not getting.
Which is not getting projected.
Like you are writing on the screen, but here the video is.
Oh.
I just.
Okay. There's some technical problem. Is it coming here?
It
No.
will come in a few minutes.
Right.
Sometime.
Okay. So using this formula, one can calculate this out. Yes, this is what it is. So using this formula, one can calculate this out. Now sine beta was known to us was 0.696. So cos 44 degree, beta was 44 degree. And therefore cos beta one can find out, cos beta one can find out. And how much cos beta is, one can find out. Cos latitude is cos 28, cos 10 minus sine 28 cos. Is this formula correct? This is cos delta cos. This should be sine actually. Just check, and cos our angle is correct. This should be cos. Yeah, so this should be sine delta. That's right. So, and this is cos delta is fine. So this sine 10 degree and sine 28 and cos how much? Cos 10 into our angle was cos 45. Cos 45 divided by cos beta is how much? No, cos of that is 0.71. So if you calculate this out, it comes out to be 104.2 degrees. So cos AZ comes out to be how much? Cos AZ is equals to, or cos phi, we might have used sometime the notation cos phi. So cos phi comes out to be how much? How much it comes out to be? This calculation quickly. This value is just 1 minute. We are checking it. Value comes out to be 104.2.
Minus 0.266. Cos phi is equal to -0.26.
Minus 0.266, and when phi comes out to be
105 degrees.
105 degree. So 105 degree, yes, that's what it is. So it would be somewhere here, 105, and because 90 degree plus 3 p.m. So 12. No, it will be somewhere there in the afternoon, and that's what it is. If the wall is in the north direction, then of course the wall solar azimuth is 105 minus 90, so that would be 15 degrees. So if the wall is facing south, if the wall is facing south facing wall, if the wall is this south facing wall, 90 degree with the north, no, 90 degree, 180 degree with the north. No, this is something wrong.
Normal to the wall makes 90 degrees.
No, the 104 cannot be there. No, so this is azimuth angle cannot be 3 p.m. So it will be more than 180 if you are measuring from north. So the cos angle will be accordingly. Cos angle will be minus 266. No.
Okay.
So it will be, inverse. This taking this inverse is a inverse one has to be careful. Inverse one has to be careful. Yeah, it will be 256 degree in fact. So 180 plus something. So this will be 256 degree. 256 degrees. So that's what it is. So 256 because 180 is this much and 3 p.m. So less than 270, more than 180 somewhere. So 256 should be the thing. Now if it is 256 and the wall is facing east, let us say, then 256 minus 90 would be the wall solar azimuth. Or if it is facing south, let us say, then it will be 256 minus 180. That will be the wall solar azimuth. So this is how we find out wall solar azimuth. Wall solar azimuth. So 2 pi is equals to 256 for east facing wall. Gamma will be equals to 256 minus 90 equals to 6 and then how much? 166, right? And for south facing wall, so this is 256 minus 180 is equals to 76. So that's how we find out wall solar, right? Wall solar. One has to be careful about these angles because when you are doing using a calculator, you have to keep in mind which quadrant it is likely to be, right? So that's it. So this is the first problem. Now the last part of this problem is again find out the incident angle. Now incident angle for an incident angle solar radiation onto a wall. Now it's a vertical wall, right? Vertical wall, and for a vertical wall, incident angle is simple because for a vertical wall, it is given by cos I is equals to, because tilt angle now is 90 degree. Tilt angle is 90 degree, right? So the tilt cos 90, wherever cos 90 comes, it becomes 0. And it becomes cos of beta and cos of gamma. So beta is 44 degree, cos 44 degree, and cos of gamma means if it is, let us say, south facing wall, then this will be 76, cos 76. So incident angle will be something like this, right? And then this would be, okay, so it's equals to 0.174. Therefore, incident angle you can find out. It will come out to, okay, so because this is a south facing wall we have taken, this facing wall, sun's projection. So basically incident angle will be normal to this wall, vertical wall, and sun ray. So sun ray is, it could be something of this kind. So I could be 79 degrees something, okay, 79.9 degree and so on. So incident angle you find out in this manner, and all the angle calculations are simple, right? Okay, so next is any question coming in between?
Yeah, one question is there.
Yeah, so there's a question would like to answer.
In TSI, how to calculate velocity inside room, or it is given the numerical?
It has to be given in the numerical, otherwise you cannot calculate it out. TSI, the formula for TSI is, if you recollect, formula for TSI is TSI is equals to, simple way is 3/4 of TW, 3/4 of TW, that's what we write, 3/4 of TD, and dry bulb temperature plus 1/3 of TW minus 2 under root B. That's what it is. Now, the question, what is the question? Question says the V has to be given, or TSI has to be, something has to be given. One unknown you can find out from here. You can't, on unknown you can find it. So inside the room, what is the velocity? If I know, then I can calculate out. Inside the room, what is the I can calculate. Or if I know the comfortable TSI, TD is known, TW is known, relative humidity is known, then I can find out also the V, right? That is for the comfortable range. Okay. Any other question?
No other questions.
All right. Okay. So let's go to a next question, next problem. Let's solve a problem again. This problem is again onto the all on this. Let's take an acoustic problem. Now, a source exhibits a sound level of 70 dB. Source, a source, so L, what you call PWL of a source, power level of a source is 70 dB. I think that was the notation we LW actually we have used. 70 dB, right? This is what you have used.
Sound level.
Yeah,
Source
sound
is
power,
PWL.
sound. Yeah, PWL. That's what we have used. So LW is equals to 70 dB at a distance of 15 meter from the source. No, this is actually source exhibits sound level of 70 dB. Okay, so this is SPL, not PWL. Sound pressure level is 70. So LP, I think we are calling it LP is equals to 70. LW is not known to us, right? At a distance of R is equals to 15 meter. So open field with a directivity is equals to, directivity is given as 1. Directivity is equals to 1, which is all directed towards that side. So what is the power level? So LP is equals to LW plus, minus 20 log R. First, let me write this, not plus. Oh, where it is gone, the pen. Plus DI minus 20 log R minus 11. Minus 11. So I want to find out this. DI is nothing but log of directivity factor, so directivity index this is, so directivity factor is given as 1, so this term is actually 0, right? And 20 log R, so this is 15 meter, so 20 log R, so this is equals to 0, so LW should be equals to 70 plus 20 log of 15, right, plus 11. So log of 15 should be 1.6 or something, right? Log of 1.6, how much is log of 1.6 or something, 1.18. Okay, so this is 1.18 into 20. So this is 23.52, 70 plus 23.52 will make it 93.52 plus 11, so source must be 104.5. So that's dB is the power level of the source. That's the power level of the source. If I want to now find out what is the pressure level at a distance of 190 meter. So if I want to find out, so I know the LP is equals to 104.5 plus 0 minus 20 log 190 minus 11. So this will be simply log of 190 should be 2 point something into 20. This is how much? This is 2.28 into 20. So make it 44 or something. And minus 11. 104 minus 34. So it will come to around 60 dB. 70 dB, sorry. No, 70, it should be less than that. This is more, 2.28 into 20, no? So it will be 50 or something. Yeah, 47.92. That's what it is coming to. But there is one catch here. You might get higher, this will be because depends upon what is the ambient. Supposing the ambient is 55, which can happen in an urban area, in that case, you will not get 47.92, but you will get 55 plus some fraction, of course, because 2 dBs you can add by taking, so dB, so SPL or LP is equals to, 10 log I by I ref. So what you can do is you can add ice. And so there's 147 dB, another 55 dB, find out the ice and add up the ice and then divide by 10 to the power, minus 12, which is I reference. And that's how we can find out the new dB, which will be slightly more than 55. If the ambient noise is 55, if the ambient noise is 55. Supposing ambient noise is around 40, then 40, it will be close to 47.90, whichever is higher, So this is a problem related to acoustics. Any question coming
There is
in?
a question related to this problem only, sir. How this 11 has come in the SPL question?
Okay, great question. Very good question. Let me just explain how it has come. I think the derivation is there in the class, but still, we'll look at it right now. Okay, let me use a new page. You see, simple, very simple. I have to go to the pen. Very simple. You see, how do you define decibel level? Either in terms of pressure or intensity. Intensity would be similar. So supposing I have a point source, sound goes equally in all directions. So at a distance r, if the power of the source is W, at a distance r, the equally in all direction, intensity is power per unit area. So W by 4 pi r square, right? But if the source it doesn't emanate sound or radiate sound equally in all direction, then I can multiply a factor which you call as directivity factor. For example, in this direction, supposing this is more, but this direction it is less. So I intensity is given by WQ by 4 pi r square. And if you know sound pressure level, sound level, SPL, or you can say L, pressure level, S level, sound level, basically what we are talking of, is nothing but 10 log I by I reference. So at a distance R, it will be 10 log WQ divided by 4 pi r square, right? Divided by I reference. Actually, the I reference would be there, I ref would be there. So now let me go to somewhere up in the page, right? So that you don't miss the bottom one. So if I do that, 10 log, I can expand this. So 10 log W divided by, let's clear it up, 10 log W divided by I ref, I can write this 2 term plus 10 log Q minus 10 log 4 pi, right? Minus 10 log 4 pi and minus 20 log R, because R square is there. So 10 log R square, 20 log R. Now this 10 log 4 pi is how much? 4 into 3.14, and this would be 12.57, and log of that would be 1.1 multiplied by 10 will give you 11. So that's how the 11 comes in. So that's how the 11. Any other question related? Okay. So let's go to some other problem. Unless somebody has got a question in the meantime. No questions. Okay. So everybody seems to be interested. Okay. Okay. Now, what shall we take? Radiation. We have taken a question. Let's say take a simple questions of calculating U value of a wall. Right. Simple question, and then we use it. Supposing I have got a 3-layered wall. Let's say this is 3-layered wall. This is, let us say, is an insulation. Say insulation like expanded polystyrene, EPS, right? And this is, let us say, some sandwich construction of concrete. Somebody has a question, how much is this relevant? In fact, these are the kind of precast construction that is coming in. Or if you go to various parts of the country, let us say today nobody uses practically, the clay bricks are getting away. And you are using actually, what you are using, aerated concrete blocks, AEC, autoclave AACs, rather AAC, autoclaved aerated concrete blocks, or air this is I'll not talk of this. This aerated autoclaved aerated concrete blocks. That's what it is. No. Okay. 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 So essentially, this, yes. So aerated concrete blocks whose conductivity would be pretty small, could be of the order around 2 watt meter Kelvin, right? Or expanded polystyrene, which will be lesser, let us say 0.05 or 0.08 or something of this kind, right? And then concrete on both sides. So this thickness is, if I say it is 100 mm, and these are 100 mm, and this is also, let us say, is 50 mm or something of that kind. Arbitrarily I'm taking, and I have a surface conductance given here, 8 watt meter Kelvin, meter square Kelvin, and this side 12.5. So H naught is equals to 12.5 watt meter square Kelvin, and this is the thickness and thermal conductivity of concrete, let us say, is 1.5 watt meter Kelvin, both sides. Then you find out the U value. So 1 over U is equals to 1 over HO plus sigma Li by Ki plus 1 by H naught Hi. So if this is L is 100 mm, and this side is also 100 mm, and corresponding thermal conductivity is 1.5, we can just calculate this out. So 1 by U is equals to 1 by 12.5 plus 100 mm is 0.1 meter divided by, I said, 1.5 plus, that was 0.50 mm we have used, something like this, 50 mm, which is 0.05, let us say 0.05 divided by 0.08 plus again 0.1 divided by 1.5 plus 1 by 8, and that's equals to how much? That's equals to 0.963. Therefore, what is the U? U is equals to 1.04. Watt meter square. So this is an insulating wall. It's an insulating wall, not very thick. Maybe partially it can bear the load also. And instead, if I have an aerated autoclave aerated concrete of let's say 0.12 or 0.17 or 0.2, 0.12, let's say autoclaved AAC block of 0.2, and same 1 by U would be 12.5, still same, and let's say it is 20 centimeter thick. So 20 centimeter means 0.2 meter divided by the conductivity, I was saying, is 0.2, and load density, say 400 kg per meter cube plus 1 by 8, and you can see that this value would be something like 1 plus 0.125 plus 0.08, right? So this is what it will come to. How much it comes to? 1.205. Therefore, U value will be equals to 1 by 1.205, 0.83. Very small, relatively. Now, supposing my temperature difference between outside and inside mean, let's say, let me take a steady situation, which is a mean in a periodic situation also means, as we have said that our temperature varies in this manner, diurnal temperature, not exactly sinusoidal, but periodic. Whatever is the 8 a.m. today temperature, wherever in the part of the country, tomorrow also likely to be similar temperature normally, except the seasonal change when that's occurring. So if I talk of the mean inside and mean outside, they nearly remain same. And let's say I'm interested in finding out the mean heat flow, that will be given by UA into delta T, where delta T is nothing but UA into outside mean, mean outside mean minus inside mean, or inside mean minus outside mean, and you can calculate this out. Now you can see that aerated, autoclave aerated concrete block will have a much lower value, 0.83, compared to the previous one, which will be somewhat higher, and normal brick would be much higher. So any further question has come?
No, sir, no question.
No question has come. Further questions? Right? No question has come so far. Okay, so that's how we can find out the heat flow through a wall under steady situation. Now let us see if I'm interested in finding out. Do you have some questions that we have been giving earlier on admittance procedure and all periodic heat flow calculations? We have been. So then I think we should some of those more complex questions we can take. So this was steady state calculation. And similarly, if I want to find out the, let's say, I know the number of air changes. Let me just take up an example of a situation of number of air changes. Let's take the ventilation heat flow. And ventilation heat flow, how do we calculate out? Simple approximate way is 1/3 N into V. That's what we have used most of the time. Actually, it is 3600 divided by 1300 or so. It will depend upon, this, I think we have talked about. N is the number of air changes. Supposing I have got 2 air changes per hour. In a room, let's say 10 meter by 6 meter, with a height of 4 meter. So how much is this volume? 240 meter cube. So how much will be this multiplied by delta T? So we've been writing as CV into delta T. So CV is this. CV approximate, but you can make it a little bit more complicated if you want. So CV then we calculate out as 1/3 into 2 air changes, 2 into 240 gives us something like 80 into 2, 160. And 160 into temperature difference, if it is mean, then mean difference temperature, let us say mean outside mean and inside mean difference is about 7-8 degrees, then CV delta T will be the ventilation difference. Okay, so this is another example. Supposing I'm interested in finding out the soil air temperature. Supposing I'm interested in finding out soil air temperature or soil air excess. And let's say on a surface which is receiving radiation, that we have calculated out earlier. We have calculated out earlier the radiation that it would be receiving, right? We have calculated it out earlier, that is radiation that it will be receiving. Okay. So any surface that we can calculate out. Actually, we have found out the cos I. So if I know the beam radiation, then I can find out I cos theta, I cos I. So that is the radiation. So if I know that radiation, let us say it is something like 200 or 150 watt per meter square. Then if I want to find out the soil air excess or the amount of heat that will come through, first how much is the temperature? So that is alpha I divided by H naught. So alpha I divided by, let's say I have an opaque surface, right? For the opaque surface, alpha is equals to 0.4. Let's say alpha is equals to 0.4. Alpha is equals to 0.4. Opaque surface alpha is equals to 0.4. And H naught is same 12 will take. So alpha, the delta T, solar air excess, will be given by alpha I divided by H naught, excess temperature. And that is equals to, let's say, is 0.4, that's, let's say, is 150 divided by 12.5. There's a temperature increase. So this would be how much? Something like, this would be how much? It is about 10, 12 or so. 12 into 4.4, 4.8, somewhere around 4.8, right? This is so 4.8 degree, right? But I want to find out the heat flow due to this. So in steady state, of course, this is all steady state I'm talking of. So that will be U area of the wall into 4.8. So if an opaque surface radiation is falling, this is what it will be, right? Okay, so this is how you can calculate out the heat flow coming in to a building under steady condition. Is there a question in the meantime?
Assignment 7, question 4, how to calculate sensible heat.
Sensible heat, sensible heat,
I got a question in assignment 4.
yeah, no. Sensible.
Assignment 7. There is another question. How to find the thermal conductivity of particular material, how it will affect the sustainability.
What is it?
How to find the thermal conductivity of particular material, how it will affect the sustainability.
No, you want to find out the thermal conductivity of the material? Well, experimentally it can be done. There are several methods. Of course, good old days people are using steady state method, what is called a guarded hot plate apparatus. We didn't cover this in our course. But there are n number of methods now. There are transient methods such as line source hot air method. Then there is a method called heat flow method. There are several methods by which one can determine. And if you look at SP41, you'll get some values. You'll get SP41, you'll get some values. But there are, good values are available also in literature as far as thermal conductivity of the material is concerned. It's a function of porosity. Good old days, people have also related it to density of the material. But more scientific would be one should relate it to the porosity. And if some idea about the solid conductivity is known, it will vary from solid to solid. One can find. So that's it. And how it's related to sustainability? Well, it is related to U value. Higher the U, more will be the heat flow or heat loss. Therefore, I don't want, what is the insulation? So 1 over U is a measure of, in a way, insulation quality. Higher the insulation in a conditioned building, energy load will be less. And in that case, operational energy requirement every year will be reduced. Therefore, total energy consumption during the life cycle of the building would be small. So this is sustainability. This is linked to sustainability. If you look at ECBC, largely it is all related to insulation only. It is only prescribes insulation, or even if any calculations you do, the insulation will play a big role. Insulation will play a big role because operational energy is related to that. Or lead rating, for example. Lead rating, you will find that energy is a major factor. The credit that you get for energy is much higher than anything else. In fact, I believe 27% in some cases. So, often I'm just saying. So in that case, higher lead rating you get when you are using lower U values or higher insulation. So K is related there. I think that answers your question. Assignment 7, question 4. What was the question?
In a room having
1.2 kg of air in total. No, this is question 4, right?
Yeah,
Total temperature is 36 degree and moisture content. Okay. So this is part of
natural.
Right. So in a room having 1.2 kg of air in total. No, what is it? 3.36 degree and moisture content is this. The desired room temperature and the moisture content is this much kg per kg. Given the specific heat capacity is 1.2 latent heat of evaporation is, assume the density of air and the above thermodynamic properties to be constant over the range of temperature considered. In a room having
Determine the amount of sensible heat to be removed from the room.
no, what is that in a room having 1.2 kg of
That is
air?
the total mass of air in there.
Okay, so that means it's, it's density of air is around 1.2. No, that's
The mass
okay,
of
but
air.
no, that's okay. But if it is 1.2 kg, which means it's a meter cube of air, that is what you are at 20 degrees centigrade. That's one is talking about. Anyway, the calculations we can easily look into. So, what was the question actually?
That's how to calculate it.
Yeah, sensible heat is fine. That's right. So, sensible heat is simple. Sensible heat issue is very simple. Let us look at this. Sensible heat is, if I call it QS, or capital QS, that will be into mass, into specific heat, into delta T. Right? Now, mass of the air flow, if I need, into specific heat, this is actually CP is rho into, this is mass into CP specific heat. Specific heat of air is around 1.24 kilojoules per kg, etc. Something like that, right? Yeah, 1.024 kilojoules per kg, that is given. And temperature difference is known to us. Temperature difference is known to us. 36 minus 27, and mass is already given 1.2, so that becomes simple. So that's how we can calculate out the sensible heat gain if 1.2 kg air is coming in per unit area, per unit time, then this is what it will be. Okay, so this is what it is. So it's simply 1.24 kg is the CP. CP is this, mass is 1.2, delta T is the temperature difference, 36 minus 27, so one can find out. Right? Okay. Any other question in the meantime? So, is there any question? Is there any question? Is there more question? So our time slot is still there or it's over? So what? So if there's no question, we'll stop. Otherwise, if there's some question, we'd like to interact more. Is there something? No? Okay then. Thank you very much. I think we had 1 hour slot that we have actually crossed. So thank you very much. Thanks for the live session. Thanks for the live session. Thank you, everyone. Sometimes I was not able to, the screen is there, the camera is here. So sometimes I was looking at the screen. Maybe I have missed you, but or you have missed me, not me. So anyway, best of luck. Enjoy yourself. Right? You can email me if there is something. Okay. Thank you. Thank you very much.